start streaming those. So if you want in your class notebook, go to 3.3b, which is called the Sun, the Earth, and the Moon. And we can get to that. By the way, I'm in the process of pasting in the 3.2 video. It was always available, like if you went to like the Teams, like just the dashboard there, because I taught it in a live meeting. I even had one person join right in, which was great. But I'm pasting it right into your OneNote, so it's right there. So anyway, in this second half, we're going to talk about exactly what it says here: the Sun, the Earth, and the Moon. I like to slide that over a bit, so I've got a bit more space to work. So the Sun, as we said, formed when all that gas snowballed into one big sphere, and in so doing, it began undergoing nuclear reactions. If you go back and watch the lesson on how stars work, hydrogen atoms, the simplest atom, bump into other hydrogen atoms, and they undergo a process called nuclear fusion, which is really fancy, but it really just means the two atoms don't just get stuck to each other. They actually hit so hard that they form into a new atom, a bigger, heavier atom. They actually, not a chemical reaction, what we call a nuclear reaction. And if you know anything about nuclear reactions, they release a lot of energy. So the Sun is just constantly an ongoing nuclear explosion that is releasing massive amounts of energy around us. That has different layers. We're not going to get into it in this course. Sometimes I have in the past, sometimes I haven't. In COVID times, I'm definitely not going to, except to say,
ignore me.
The Sun has, hello, how are you?
Quick little off-topic question.
Please.
Would you have a USB-C to Ethernet?
Yes, I do.
No way.
Yeah,
oh, no way. Can I borrow it for like 2 hours?
Give me a sec.
Come on.
Give me a sec. Where is it? It might be the microphone that Marcy's using. Give me a
That's
sec.
wicked.
See, this one's nicer than mine.
Where is this one?
If you're using it though, don't worry about it.
No. Give me the sec. This is USB-C. Which one's mine? Oh.
Don't worry about it.
No. I 100% have it. It is the one I have in Marcy's room. But. I have my regular old USB Ethernet here, but I also have a USB-C adapter. So now that's not C.
And then
I've got like a little dongle.
Yes.
Where is that? I know it exists.
You can count on Mr. Orlando for obscure.
Oh, whose laptop is that on right now? That is
Okay.
on someone's laptop right now. Yar! That was my pirate frustration voice.
This might work.
Okay, try that, and I will find the other.
This might work.
Somewhere have
This
an
might
adapter.
work. I'm not going to tell you guys what it's for because you'll laugh. Thank you, sir. I'll see you.
Okay, if that doesn't, I will find the other. Just let me know. Okay, the Sun has distinct layers, and the reason it has distinct layers is because in its formation, there are places, the core is mostly dead matter. That is matter that has already collided and be used up. Does that make sense? And that settles to the middle because it's heavier. And then as you move up, you get the radiative zone. That's exactly what it sounds like. This zone here is where the actual reactions are happening. Beyond that, we have a zone that actually isn't hot enough to be burning itself. We call it the convective zone. This is where that heat moves through and moves out. But so like this portion of the Sun here is the portion of it that is actively undergoing nuclear reactions. This part isn't because it's already done. It's been used up. It's spent fuel. And this portion isn't because right now it's not hot enough to do so. Does that make sense? We're not going to get into that. But just something to be aware of. The Sun has distinct layers, they're shown above. Would I normally do a lesson where we talk about the Sun in more detail? Yeah, it's fun, it's cool. But I feel like I've done my piece, we'll move on. So does the Earth. But what I want you to know about both of these is that the reason they have these layers is that these layers tell us about the history of how they formed. Does that make sense? Why is the Earth a big lump of rock? Why is its inner core incredibly dense and hot? Why does the zone above that, the mantle, why is it hot enough that it is liquid rock? Because liquid rock is a weird thing to think about, isn't it? Imagine taking a rock, And imagine getting it hot enough that she melts. It's pretty hot. Why?
Well, because of gravity and what you said about fusion and stars and how gas
You're doing great.
converts into stars. It does the same with planets.
Bingo.
Except it's a lot more, I guess,
Bingo.
faster. Or
That's right.
a lot more.
Yeah. Again, just like the way the stars formed, that all that friction heats it up, they get big enough eventually that they become a big nuclear explosion. Our planet does not get big enough to become a big nuclear explosion. That's still the same process. It still was rock colliding with rock, colliding with rock, building up, building up, building up, and that's a lot of friction. And, hey, you ever cook a potato? Sometimes you cook a potato, you got potato, it's nice and hot. You ever eat like baked potatoes, you're just eating the thing whole? You leave it sitting out a bit, it's still hot. Are you still heating it? No, but it's still hot because it still has that heat energy and it has to slowly radiate it away. Why is the outside surface of the Earth nice and cool? Because it's able to radiate away that heat. The center of the Earth, on the other hand, is still hot. It's crazy to think, 5 billion years later, the center of the Earth is still hot from the heat it had when it first formed. It's still just cooling down. That's how long it takes a planet to cool down, because it's a big old mass of rock. Eventually, Earth will be soaked up by the sun and destroyed. But if it weren't going to be soaked up by the sun and destroyed, which is what will happen, it would cool down. It would cool down. Eventually, it would just become a big, boring, old, cold rock in space. But it's not right now. We have this little thin surface we call the crust that's nice and cool, and underneath that is a big raging torrent of melted rock because it's really hot from when it formed. We are little islands of rock on top of a big ocean of hot, burning, melty rock. It's crazy. Crazy, crazy, crazy. And it's a function of the Earth's formation. Does that make sense? You're not just nodding to shut me up? Okay, that's good. So we don't want to get too much into that, except to say the liquid mantle and dense core provide evidence of how Earth was formed. And again, you could teach a whole course on just that. I'm not going to talk about it because A, I don't know enough to talk about to teach a whole course. I'm not that knowledgeable. I know just a little bit. But secondly, obviously time doesn't permit. But it's a really fascinating topic. There's a lot to unpack there. Okay. So that's all we're going to say about that. And then I want to get into the actual nitty-gritty mechanics of how does our solar system work? Why do we see the things we do? Why do we experience the things we experience? And so the first thing to know is because the gas accretion disk, gas and rock and rubble accretion disk from which we were formed was spinning, everything in the solar system is also moving in circular paths. Does that make sense? We experience that in two different ways on Earth. What are the two ways in which we still today experience that early rotation of the formation of our solar system? What are the two ways that Earth is still affected by that? That's okay. That's okay. But give it a try. Worst case scenario, you're wrong. I'm wrong 238 times a day, and it doesn't stop me from talking all day. Yeah.
How day and night works?
Day and night. Why does day and night work? We're facing the sun for a while. Then we're not facing the sun for a while. Then we're facing the sun again. What's going on? What is the Earth doing? You're totally right. I like it.
I don't remember which one it is, but it's either because we're rotating around the sun or the Earth itself is spinning.
Good. Those are the two things. So that's great. We're going to break this down. There's two things going on. Because of that spinning motion of the forming solar system, the Earth is moving in two circles. The first way it's moving on a circle is that it is rotating. It is doing this. Isn't that fun? That's the rotation of the Earth. The other thing it's doing is, this is plugged in. Oh, but I can do it. Aha. Aha. Oh, I have the power. So it is rotating, but it is also, yeah, I'm the sun. What's it to you? That's right. It's also orbiting around the sun. It does both of those things. Those are two circular motions. Does that make sense? They're both circular motions of a different type. And they're both the result, yes, sir?
I just noticed something. You said earlier that the Earth is like tilted 23 degrees. Is that why the globe is never?
Yeah, very good. That's exactly right. They put the tilt on this because the Earth's rotation is tilty. So why not, right? And doesn't it look nicer that way anyway? But that's right. And if you measure this, if it's a well-made one, it'll be 23 degrees.
Is that also why we have seasons?
Ah, yes. We're going to get into that in a moment. But yes, absolutely. Yep.
Why north is cold and the south is hot?
Well, no. We'll talk about that. But you're on the right track. You're both on the right track. You're thinking really well. You guys are so clever. So let me ask you, how long does it take for Earth to do this? How long?
23 hours.
20...
3.9.
24. Stop being difficult. It's exactly 24. We'll talk about that. It's exactly 24 because we define 24 hours as the time it takes Earth to do this. Now, you're thinking about something called a sidereal day, which is its own interesting topic because while it's doing this, it's also doing just a little bit of this, right? But that's okay. We'll get into that. Yeah, it takes 23 hours for this to happen. So the Earth revolves on its own axis. And an axis just means an imaginary line going down the middle of the planet. The Earth revolves around its axis. Revolves around its axis. Every 24 hours. Which, for the record, a planet's a big old thing. It takes a lot of energy to spin that thing all the way around in just 24 hours. A lot of material. Big thing. The direction it does so, if you look at the Earth from above the North Pole, which is usually what we do. We tend to think of north as up and south as down, right? Because we're elitist imperialists and we think of like Europe as the center of the universe. So for that reason, we think of north as up and south as down. And if you think of it that way, so if you look from above the North Pole, Earth rotates in which direction? Well, let's look here. If we were to look down from above the North Pole, right? Yeah, I remember my power. We look from above the North Pole. Let's make sure I get it right, because sometimes I don't. It goes this way. Is that clockwise or anti-clockwise? Yeah, very good. Earth rotates anti-clockwise.
I've never heard anyone say anti-clockwise. I always hear counterclockwise.
Okay, well, you can write counterclockwise if you like. Both are fine. And as we say, this is actually quite a nice demonstration. Can you guys see one side is bright and the other side is dark? This is how we get our day. So on this globe right now, what continent's in the middle of the day? Africa, Europe. And now it's midday for them. Now it's morning and dawn for Canada and the US. Can we see that? As they are starting to go into darkness. And now it's the middle of the day for us, and it's nighttime for them. And it goes on and repeats and repeats and repeats. Can we all see that? That's why when it is daytime for us, it is nighttime for the Chinese and the Indonesians and the Japanese and those who live in India. They are on the opposite side of the earth. So when the Russians, when the Eastern Russians are having their nighttime, we are having our daytime. Makes sense, right? This gives us day and night. Do I need to write a sentence explaining why it gives us day or night, or does the fact that it rotates, and so sometimes you're facing the sun and sometimes you're not, is that obvious? Don't be shy. I don't want to write too much, because I don't want to waste your time, and I don't want to write too little and then you're confused. So you can talk to me. But my instinct is to leave it like that. How do you feel about that? That's probably something you at least kind of already knew. Maybe you've talked about before, maybe you haven't, but you probably have a basic understanding of that. So that's one of the two rotary motions that's baked into the Earth, is that it rotates, seen from above, in an anti-clockwise direction, and as a result, and this, by the way, is why we see the sun always, quote-unquote, rising in the east. It's not that the sun is rising anywhere. The sun isn't moving. I mean, everything's moving. Motion is relative. But the way we usually think of it is the sun is in the middle of the solar system, and it's not that it's moving, it's that we are rotating towards it. And so the reason it appears to rise in the east is because the Earth is rotating to the east. Does that make sense? We're rotating in that direction. So we are moving into the sun's light path, and we see day, and then we eventually rotate past it, and we see the sun set on the western side, and then we see the night, because we're rotating. This is also why, has anyone ever gone stargazing? Anyone ever gone out and looked at the stars at night? Because if you do, and you should, because it's amazing, but if you do, what you'll find is that if you're watching a certain star in the sky, over the course of the night, just like the sun moves across the sky in the day, all of the stars move across the sky in the night. They move, except the ones that don't. But they all move in the sky at night because they aren't actually moving. We're moving. We're moving, 360 degrees every 24 hours. Hey, could you do a little math and figure out how many degrees they move every hour? I bet you could. A little more math and figure out how many degrees everything moves in the sky every minute? Sure you could. That's what our time system is based on. Our time system is based on the fact that we know that if you go outside and watch the stars, they move a certain number of degrees every minute, every hour, every day. Yeah.
So there's this app you can get on your phone, and if you're looking at the stars,
isn't that great?
It uses augmented reality to see which every star is.
Yeah, there's a bunch of them, like those Night Sky, those Star Tracker, there's a bunch of those, and they are all magnificent. And how cool that you can go out and just look up and see what's there. You know, right now, you are getting the best Mars views right now that you will get for a decade to come. Mars in the sky right now, in about a month and a half ago, it was at its absolute brightest, but it's still super bright. So next time you have a clear night, go out and look. Mars right now is like a little bit ahead of the moon. So like, you know, the moon will rise in the east and set in the west just like the sun does. If you look right now, a little bit lower down and a little bit further on in the sky, you'll see a bright star and you'll be like, hey, is that star red? And the answer is it's not a star, it's a planet, it's Mars. Yes, it's red. Yes, you can see that's red with just your naked eyes, which is crazy. And it's just beautiful and bright right now. Saturn's pretty good right now. If you get up early in the morning or late at night, you're seeing a bit of Venus right now. Great stars in the sky right now. Go and look. It's pretty cool. Yes?
Does an hour having like 60 minutes and not 100 minutes something to do with rotation?
Yes and no, which is to say this. The same reason we have 360 degrees in a circle, which is a stupid random number, is the same reason we have 60 minutes an hour, which is a stupid random number. And the answer is that both of those come from the same culture's counting system, which I want to say Babylonian, don't quote me, Calford would be the guy to ask because he knows about all this stuff, but the same people who give us our way of counting how many degrees are in a circle are the same people who give us how many minutes are in a day. But yes, our time system, our calendar, everything is based on the Earth's rotation and the Earth's revolution. And as we'll see, what the moon does. The movement of the Earth and of the moon are what our entire time systems are based on. Which makes sense because there are these things that do the same motion over and over and over again, and they do it in a really predictable time. So the Earth doesn't just rotate the Earth also revolves. All right, and revolving, revolution, means turning around something. So rotation is just on your own axis, right? If you're the figure skater and you're like doing this thing, you know that thing, what's that called? That was that was elegant of me, right? Were you all pretty impressed? No big deal. But that is rotation. When you go around something, like when they are just going around the rink like this, we call that revolution. You revolve around something. I think that the whole world revolves around me. But like when you move around something, you are revolving. So this movement is rotation. This movement is revolution. Now, in what direction, if we looked from above again, do we think that revolution of the Earth would happen? We said the rotation happens counterclockwise. What do you think about revolution?
Counterclockwise as well.
Yeah, why do you think it's going to be the same? You're right, like you're totally right, of course. Why is she right? Why does it have to be the same? What do you think? What do you think? Well, because why are they spinning in the first place? Because that's how they were. Yeah, that's how they were formed. That's how they were made. So that spinning is just left over from their creation. And so they continue to move in that same direction. So Earth revolves around the sun. Anti-clockwise, as seen from above. It takes 365.25 days to do that. When we say it takes 365.25 days to do so, what it means is this. The Earth is able to do this 365.25 times in the time it takes to do this. Does that make sense? It's always doing both at the same time. It's doing this, and it's doing that. I'm not very coordinated, so I can't really get them both happening at the same time. I'm sure somebody more athletic than I could. It's always doing both, and it's able to do this 365.25 times in the time it takes to do that once. And what do we call then that 365.25 days? We call that a... Yeah, this is where the idea of a year comes from. 1 year is one trip around the sun. 1 day is one trip around your own axes. That make sense? That's a day. That's a bunch of days. That's a year. That is a bunch of gross wax falling on my head. All right. It's a candle. It's got like a little thing in here. Not like a candle, but one of those like melty, waxy things you put in and they're supposed to smell nice. Yeah. That's all. Okay. Let me ask you this. We know that a year happens because we move around the sun. How did they know in the past that a year had passed? Seasons. That's one of the two reasons. Very good. The seasons tell us that. We're going to talk about seasons in a minute. So I'm going to skip them for now, but that's true. What's the other thing? You might, yeah.
They decided, I want to know this, so they were like, let's count every day.
I like that. But what were they looking at? If we didn't have seasons, the seasons are enough that we could have figured it out. But there's something else. And you might know this about yourself. You might know that you're a Leo. I know that I'm a Leo. What does that mean?
Oh, what was it? You were born on month I forgot.
Yeah, I'm born in July, and I'm born in the month that Leo becomes visible in the night sky for the first time. That's why we say you're a Leo, because the constellation Leo shows up for the first time around about my birthday. Happy birthday, Joe. Here's Leo. But here's why. If you imagine, there's like some stars here, and that's a constellation. And there's some stars here, and they look like a shape, and we say that kind of looks like a crab, so we call it a constellation. And then there's a bunch of stars here, and we're like, that kind of looks like a goat. All right, that's a constellation. That looks like someone hunting. Oh yeah, that's a bear. Oh, there's, like, what are the other ones? Virgo, that looks like a virgin. I don't know, these things are weird, right? Well, what? It's true. Don't blame me. I'm not the one that looked at stars and was like, a virgin. I don't know. I didn't make it up. And then they see this one, and it's like Capricorn. I don't even know what that is. That looks like a Capricorn. And this guy looks like what are the other ones? Sagittarius. That's the guy on the horse, right? Like the hunt. I don't know. So there's all these things, and they look up. And why do we care? Well, they're all around us in space, right? But here's the thing. What time of day can you see the stars? What time of day can you see the stars? What time of day can you not see the stars?
Daytime.
Day. So, when you are on this side of the sun, when we're over here, I can see these stars, and more to the point, over the course of a night, I can see all of these stars, right? But I can't see any of these because they're blocked out. Because what blocks them out? No, the sun, right? Because when I'm rotating, everybody on the Earth at some point during the day is going to get to see all these guys, but nobody, no matter where you are on Earth, is going to get to see those guys because the sun is always there. Does that make sense? And just like with this shining in my eyes, if you like went and put your cell phone up there with like a message written on it to me, if you was like, you suck, Orlando, and you put it next to the projector, I'd never know. You could totally say it, because why wouldn't I be able to see your little screen up there? Why am I actually doing this? As if it was necessary for me to really stare into the projector to make this point. Now I'm seeing just big blue streaks all in my vision, but I might have a seizure, is what I'm saying. But why wouldn't I be able to see your screen up there? Because I was staring into the projector. It's too much light. Your screen wouldn't be bright enough for me to see, right? All of these stars, when we're on this side of the planet, I can only see these guys. I can only see some of the constellations at any given point in the year. Does that make sense? If it is springtime, and I'm here, then I can see all of these constellations, but I can't see any of these constellations. Does that make sense? If it is wintertime for us here, then I can see all of these constellations, but I can't see those ones. So over the course of the year, the stars that you can see in the sky change, because the ones that are on the opposite side of the sun from us are invisible, because during the daytime we see the sun, we can't see the stars. And the ones that are on the dark side of us, we can see those, because it's nighttime. And so what ancient peoples were able to discover is that, oh man, every 365 days, that thing becomes visible again. And then we can see it for a bunch of days, and that disappears. But like clockwork, 365 days after the first time I saw it, I see it again. And that's true for every single star. They disappear, but if you count the first day you were able to see them, it's always exactly 365 days later, 0.25, that you see it again. And so what do they conclude? They're smart. They know. The Earth must be going around the sun's blocking these stars out, and the time it takes to make that trip around the sun is 365 days. Does that make sense? Cool. So I'm not going to write all of that because that would take a lot for that, but we can say, as a result, only half of the stars in the night sky and I'm just going to say it gradually changes, which is to say which stars are visible and which stars are invisible gradually change as the Earth makes its trip around the sun. That and the seasons was enough evidence for people 2,000 years ago to say, oh, Earth's making a trip around the sun. That makes sense. We can figure that out. More than 2,000 years ago, 3,000 years ago. 2,500 years ago, somebody calculated how big around the Earth was. 2,300 years ago, somebody calculated how far away the moon and the sun were from us. There's smart people in the past. They didn't have any technology, and they were able to figure this stuff out just by looking up at the stars. How did we figure out the Earth was round? Well, it's a discussion for a different day. We'll get there. But literally, again, by looking at the stars, by moving from one place to another and seeing how the stars changed. That was all the information they needed. It's amazing what you can learn about the world around you if you look, if you ask questions, if you write things down. If you just make careful observations, you can discover incredible things. This is what they discovered. Now, somebody, and I'm forgetting who and I'm sorry, mentioned the seasons. And yeah, the seasons are the other thing that tells us that it takes the Earth a year to trip around. Why do we have seasons? Who do we get to thank for our seasons? No, actually. Thea. We can thank Thea for our seasons. Because what happened when Thea hit us? We went from being nice and upright, good, upright, orbiting people, going around the sun, and when Thea schmacked into us, what happened? Yeah, that's right, big old uppercut. Planet Earth just got knocked out, but you should see the other guy. He's my moon now. What happened to him?
He became limp.
He's tilted. He got knocked a little bit out. He's never quite been the same since. Tilted. And that tilt ends up being really important because with that tilt, even if it's daytime, depending on my tilt, right now, I'm facing the sun, it's daytime. Who's getting more sun? Right now, the way I have the Earth here. North America or South America? North America. Why? Because North America is tilted towards the sun. And South America is tilted away from the sun. And it doesn't matter what I do. As I rotate, now who's getting more of the sun? Northern Europe or Southern Africa? Northern Europe, because they're tilted towards the sun. You see that? So for the whole time we're tilted this way, the north is getting it. But then when we rotate, if I rotated the other way, now this doesn't shine in every direction. So can I simulate it? So we spin around and I'd actually have to be behind the projector. But it's essentially going to look like this. Now, who's getting more sun? North America or South America? Can you see it? The sun is shining right on South America, and North America is just getting like a wee little bit of sun down there. Hardly any at all. Does that make sense? That's what summer and winter are. In fact, you want to know something funny about living in the northern hemisphere? Do you know when we are closest to the sun? January. January is actually the point in our orbit when we're closest to the sun, right in the middle of our winter. But our winter isn't a function of being close or far from the sun, because our orbit's almost a perfect circle, right? Because that's only a little bit out. We have summer because during that time, that 23-degree tilt has us tilted towards the sun. And we have winter because at that point in our orbit, that 23-degree has us tilted away from the sun. Does that make sense? Cool. So we're going to say that. Oh, and I had a video. See, you didn't have to listen to me talk. Let's watch this, because somebody worked hard on this.
You know that Earth orbits the sun, right?
Yes.
And that it takes a full year for our planet to complete its orbit?
Oh, you betcha.
Earth also rotates like a slightly tilted spinning top. Earth remains tilted in the same direction all year round as we orbit the sun. But that means the sun's light shines differently on Earth at different times of the year. Let's look at Earth when it's winter in the northern hemisphere. Observe how the North Pole tips away from the sun. This means that sunlight strikes the northern hemisphere at a shallow angle for a short period of time. This is why winter weather is generally cool, with short days and long nights. As Earth orbits the sun, we move towards spring in the northern hemisphere. Now Earth is tilted neither toward nor away from the sun, as day and night are about equal in length. As we make our way to the summer months, notice that Earth is still tilted in the same direction, only now on the other side of our orbit. The North Pole is tipping toward the sun. Sunlight strikes the northern hemisphere more directly, and the sun stays in the sky for a longer time. Compared to winter, summer days are warmer, and the sun stays in the sky much longer. Notice too that while it's summer in the northern hemisphere, it's winter in the southern hemisphere. Because of Earth's tilt, the seasons are reversed. We observed how Earth's tilt creates the different seasons throughout the year. How does this affect life? Plant life and other photosynthesizers, we call them primary producers, depend on sunlight. They respond to the changes in the seasons. Earth-orbiting satellites measure the amount of carbon dioxide absorbed by these primary producers. Bright regions on this map show where they devour the most carbon dioxide, turning light from the sun into oxygen and natural sugars. In spring, when sunshine strikes the cold waters of the North Pacific, productivity skyrockets. Phytoplankton and other microscopic photosynthesizers form the base of the ocean food web, and all ocean life responds to changes in the seasons. On land, forests grow green during the spring, brightening the continents. During winter, continents in this view turn dark from a lack of photosynthesis.
Let's see why I added that video. I like that video. So, Earth's revolution around the sun gives us seasons because of its 23-degree tilt. And are you ready for some amazing art? Try not to be intimidated because I know that I'm a really good artist. So this is the sun. See, and I'm going to show that like that. Yeah, I know, it's good. It's really good. And then this is going to be the Earth's orbit. Now, if I was viewing it straight from above, of course, it would be a perfect circle, right? But I'm kind of, well, not perfect, but really close to it. It's an ellipse, but it's really close. But I'm kind of viewing it from like an angle. So then we're going to say, okay, here's the sun, here's the Earth. Okay, there's the Earth. And like I'm going to, whatever, we're going to say when it's on this side would be nice and bright, right? And then the back side of it, well, it's going to be kind of dark and just in shadows, right? But remember, the Earth is tilted by 23 degrees. So that's north and that's south. Can you kind of picture that? And then when we get to this side, the Earth is still tilted north to south, just like that, right? There's north, there's south. And it's still the case that this side of the Earth and I guess actually I should draw like the equator on here too so we can really see it. Everything above that dotted line is in the northern hemisphere. Everything below that dotted line is in the southern hemisphere. And so now, having given you not a lot of information, which one of these is summer and which one is winter? It can be a little tricky at first. which one of these is summer? Which one of these is in winter? If for the north, for us, because we're in the north, right? Canada's in the northern hemisphere. So which one of these two are we in right now that we're coming into winter? Yeah. Yeah, because if you look here, for the north, this is winter because if we imagine sun rays coming in like this, the north is just getting a little bit of that sun. Can you see that? Just the bit above this dotted line. And the south is getting tons of it. Does that make sense? So for us, we experience this as winter, and those South Americans and, Australians and South Africans, they would be experiencing summer. Right? Summer where the days are long and where they get lots of light. Winter where the days are short and we get just a little bit of light. And as a result, long days with lots of light means hot. Short days with a little bit of light means cold. Okay. That means here, if we imagine being rays of light like this, above the equator is getting lots of it. Below the equator is just getting a bit of it. So for the north, we would call this what? That didn't need to be 6 feet long. In the north, we would call this summer, because we get lots of it. And in the south, they would call this winter. Does that make sense? Now, when we go from summer towards winter, in the middle, what do we get? We go from really long days to really short days. So when we are here, even though that tilt is there, it doesn't really matter because this whole side is getting all the same amount of sun, right? So even though it's tilty, it doesn't matter that it's tilty because the whole north is getting the same amount of sun as the whole south. Does that make sense? If you're a beam of light here, you're just hitting all of it. Everything gets an equal amount of sun, right? And so at that point, we would say that the north is in going from summer to winter. What do we call that? Fall. Right? It's starting to cool down because we're getting a little less sun than we were in the peak of summer. On the other hand, for the southern hemisphere people, they are getting more sun than their winter months, though not as much as they'll get in the summer. What are they experiencing? They're getting more sun, but not yet summer sun. What do we call that? Spring. Good. And then to say the opposite, right? This whole thing is getting the same amount of green. And then to say the opposite on this side, where again we're still tilted, but in this case, the side that we can see is getting the same amount of darkness and the other side's getting the same amount of brightness. Here in the north, if we're going from winter to summer, what are we experiencing? Going from winter, heading into summer. Now the north is experiencing spring. Good. And our friends in the south would then be experiencing... Nope, we're experiencing spring. They're going from summer to winter, so they're experiencing fall. Good. I know, I'm good, right? Yeah. Just so you know, you obviously can't draw this, so I gave you this diagram over on the right. If you scroll to the right, don't worry about it now, but at some point, go drag that to where it goes. I gave you a copy of that, but I thought I would, give you all my beautiful art.
Do you have that box of medium gloves? I'm totally out and small. I can't get my face.
Yes, if you go into the first cupboard there.
When you say first cupboard, they're like.
If you go to the far benches. Yep, and then closest to you. You're right close to it. Yep, that one there. It's either in that first one or maybe the second one over. And I might have some in here too.
Oh, good. Yeah, I need medium. Thank you.
No problem. And Joe has ordered some, so it's just a
Okay,
matter of going there.
I'm taking a wee box.
Nice. And I have some large ones and some small ones here if you need them as well.
There, you have a full medium back there.
Nice.
I'm taking this one with.
Do you need large or small?
No, this is fine for now.
You're okay?
Yep, thank you.
All right. Okay. And then there's 4 dates to know. This exact date, this one here, when it is as wintry as winter can be, the shortest day of the year, the day when we get the least sun and the most dark, what day do we call that? Does anyone know? The shortest day of the year. It's obviously going to happen in what season for us? Yeah, and by the way, these are for the north, all right? Because for the south, they're the exact opposite. But on or about December 21st, it can be as late as the 23rd, we get the winter, what? The winter, anyone know this word? Anyone heard that? No? Oh, good, I've taught you something. Had to happen eventually. That's right, this is the shortest day of the year. All right, so on December 21st, 22nd, 23rd, right around about there, if you count how long the sun is up, that is as short as the days get. After that, every day gets a little bit longer, which is nice. Until what's on the opposite side of the sun is the opposite side of the calendar. What is, obviously, if this is the winter solstice, what's the other one we're going to be talking about? Sorry? Very good. So June 21st to 23rd. It depends. It changes a little bit every year based on our calendar, but roughly. And what's it going to be called? Very good. If somebody can do a spell check on solstice for me, I'm having a moment now. I'm not feeling. See, I should have known that. I accept that correction, and I apologize for having had it wrong. Solstice. Silly Joe. There we go. And if that was the shortest day of the year, this is the longest day of the year. Again, in the north. In the south, they are experiencing the exact opposite, right? Hey, where does it not make any difference? Where could you live where it would make no difference? If you live right on the equator, every day of the year is the exact same length, because you, being right in the middle, are never tilted towards or away from. You're always getting equal amounts of sun and light. Now, right in the middle, this day where it's equal, what do we call a day? Let's do this one, the fall one. Actually, let's do this one, the spring one. Let's do this one first, actually. We'll do fall. In or around September, we get what is known as the autumnal. Autumnal just meaning in the autumn. And autumn is another word for fall. What's this word? Equinox, good. Equa means equal. Nox means night. Equal night. So this is equal night and day. Right in the middle, you get a day that is perfectly night and day. And so we call that the autumnal equinox. Sometimes they just call it the fall equinox, but the proper name is the autumnal equinox. And if that happens in the fall, it's also going to happen in the spring. Can anyone get the date for that on me? What do we think? If it's halfway between winter and summer, what's the date going to be roughly? Okay.
March
Yeah, and again, that's this year. I'm going to put 21st because it's roughly the 21st, but it does change every year. And what's it called? The fall equinox is known as the autumnal equinox. This one is known as the...
Spring.
Yep, and sometimes you'll see the word vernal equinox. Either is fine. I'll put spring. Can you Google vernal for me? Get a spelling for me. Vernal equinox. I think it's Vernal, but there we go. And that is also equal day and night. Again, do I really care that you have these dates memorized? No. You can always Google it, right? You can just ask. But I do care that you understand why they exist. That makes sense? That's important. Understand why, because of that tilt of the Earth, sometimes the south gets a lot more light than we do. And so they get hotter than we do, and they have longer days than we do. And other times, we get way more light than they do. And in that situation, we call it winter. Does that make sense? All right. So that has to do with the motion of the Earth. The Earth rotates, and the Earth revolves, and that gives us day and night, and it gives us the seasons, and it gives us different stars in the night sky. But the Earth isn't the only thing that's rotating around something, revolving around something, I should say. What else is revolving around something and rotating?
The moon.
The moon. And can I tell you, before we get to it, the moon, there's something super cool about its revolution that you've probably never thought of. Maybe you have thought about it. I know I hadn't till I was taught it. But when you look at the moon, so we know that because the Earth rotates, sometimes we're facing the sun, we call that daytime. Sometimes we're facing away from it, we call that nighttime, right? And so the sun is always seeing different sides of the Earth, right? Does that make sense? Because of the Earth's rotation, the sun is always seeing different sides of us. Wow. I like to think they're having some sort of feats of strength competition up there, yes.
It's like that one commercial where there's like the clog dancers in the upstairs apartment.
I like it.
Someone's wrestling up there.
Yeah. So, because of the rotation, the sun always sees different sides of us. Have you ever looked at the moon and seen a different side of it? Think about that for a minute. Have you? You've seen it be different shapes, right? Sometimes it's fully bright, sometimes it's partially bright. But have you ever looked up and seen like different features? I'm going to challenge you to think about it because I bet you haven't. In fact, even better than that, do you know that the other side of the moon has like a crazy different shape? Because if you think about our side, if an asteroid were going to hit the side of the moon that faces us, what would it probably hit first? This is the same principle by which umbrellas work. When you put an umbrella above you, the idea is that any rain that's heading towards you, what's it hit instead? The umbrella. Well, if an asteroid was going to hit the moon, what's it likely going to hit first if it's coming by Earth? The Earth. But if it comes from the other side, then can it hit the moon? Maybe, maybe not, but easier, right? We're not blocking it. So one side of the moon, the side we see, is fairly smooth looking. Right now, Google a picture of the far side of the moon. Yeah, Google a picture of the far side of the moon. And see what you get. I can't because for some reason my keyboard is behaving very strangely. Yeah, do you see how much more cratered it looks? Isn't it wildly different? Now I promise, you've never looked up and seen that side of the moon, have you? You ever looked up and seen the moon looking like that? No. So what's going on? Why do we only see one side? Does the moon not rotate? Sorry, does it not revolve? Does it only rotate around us? But even then, that would mean that we would see one side of it, and if you lived on the other side of the planet, they see the other side of it. Is that true? If you live in China, do you see a different side of the moon than we do? No, I think I'd know about that, right? So what's going on? There's a really cool thing. How long, does anyone know how long it takes the moon to make one orbit, one revolution?
31 days.
Close. If the universe made any sense and how we named things, yeah.
27 days.
Close, 28. 27 and a bit, but roughly 28. It takes roughly 28 days for it to do one orbit. Now you want to know something really cool? How long does it take the moon to rotate on its own axis?
31 days?
No,
Aw.
28 days. Exactly the same. The moon is super cool because its revolution and its rotation are locked. They do it at the exact same speed. The result of which is that from our perspective, we always see the same side of it, because as it's going around us, it's also rotating so that it's showing the same side to us, and that lock is perfect. We call it a tidal lock. The moon is tidally locked, which means that its rotation and its revolution go at the exact same speed, and they're locked into one another. I have a little video about the moon I'm going to show you. Yes?
Would that explain the moon?
Canadians are
Sorry.
responsible for one.
A.
Would that explain the moon is watching you, kind of?
Canada. A.
Hey! That's my hometown, Niagara Falls.
Yeah, I was actually
And my hometown
Were
is
you?
St.
Me too. Okay. No, I don't want YouTube Premium, and I don't want to stop. See, look at that.
YouTube Premium is not worth it.
Okay, so let's take a look. Let's see what they have to say about the moon.
Over 150 moons orbit the solar system's planets, and one of those moons calls Earth home.
The moon.
The moon was formed about 4.5 billion years ago, when, according to one theory, the Earth slammed into another early planet. Debris from this collision began to orbit Earth and accumulated, forming today's moon. The moon is the fifth largest natural satellite in the solar system, with a diameter just under the width of China. It's composed of an iron-rich core, plus a mantle and crust containing minerals made of magnesium, oxygen, and silicon. The moon's surface was once geologically active and covered in an ocean of magma. But today, apart from traces of water ice, the surface is completely covered in dust and rocky debris. Countless craters dot the moon's surface, each formed by objects such as meteoroids, comets, and asteroids crashing onto the moon.
Because there's no
The
air, it
largest
never
crater, the
gets
South
disturbed.
Pole Aitken Basin, spans across a quarter of the moon's surface and is nearly deep enough to fit Mount Everest inside. The moon orbits our planet at an average distance of 30 Earths. It rotates at the same rate that it revolves. So as it revolves around our planet, the same side of the moon faces the Earth at all times. From the Earth's surface, we can observe 8 distinct, traditionally recognized stages of the moon's illumination. Called lunar phases, they have been observed for thousands of years and even provided the basis for the earliest calendars. For most of human history, the moon could only be studied from afar. But on July 20th, 1969, humans were able to close that distance with the American spaceflight mission Apollo 11.
That's one small step for man, one giant leap for mankind.
It placed humans on the moon for the very first time, bringing our understanding of Earth's only natural satellite one step closer.
Alright, so that's a little bit about the moon. We'll write a couple of things down. Not too much, we don't want to go nuts. But key points to know. Moon revolves around Earth. Every 28 days for one revolution. Also rotates once every 28 days. So we always see the same side. Those are really the two big things. By the way, our calendar is based on the moon, but somewhere along the line we screwed it up. Do you know how many months would we have if each month was 28 days? Does anyone know? Anyone do that math? 365 divided by, instead of dividing it by 12 months, divided by 13, what would we get?
28.7.
Yeah. So in other words, if we had 28 days in a month, we could have 13 almost perfect months. And all we would have to do is add on 1 day 3 out of every 4 years. So like the opposite of our current leap year system where we add 1 day. You know what I mean? So think about that. 13 months works almost perfectly, and then all the months could just be 28 days instead of the chaos, the nonsense we have of like 30, 30, 31, 28, 30, 31. Craziness, right? And they would line up with the lunar cycle. But for some reason, that's not what we do. Instead, we have 12 months. And then, have you ever stopped to think about how crazy our month names are? Why is an octopus called an octopus?
Oh my god, it was discovered on October.
No! Because it has 8 legs. And octo is Latin for? 8. And October is, of course, the 10th month of the year. 10th month of the year, because we're stupid. November comes from novo, which is Italian, well, Latin, but Italian carries it now for 9, neuf in French. So November is, of course, the 11th month. And December comes from deca, where we get 10 in French for 10. And so December, 10 ember, is, of course, the 12th month of the year. Yeah, our calendar sucks. It makes no sense. That's the end of my rant.
Sorry to interrupt.
Yeah.
Do you get infuriated when I interrupt you?
No.
Okay, good. Sophia. Okay. This is for you.
Oh, there we go.
So if all this checks out, you don't really need to do anything with it. And then if something isn't right, just change it and bring it back to Miss Orlando. I just need to... Sorry, I really do.
Can we all say hi, Mr. Trush, like we're a kindergarten class? Can we do that on the count of 3, right? 1, 2, 3. Hi, Mr. Trush. You guys suck. That was terrible. Do you think he feels welcome right now? I wouldn't feel very welcome. I'd feel like you guys didn't even want me here.
I'm an intruder. You're teaching hard, and I'm just grabbing all this stuff.
If I were Mr. Trush, my feelings would be hurt, and then I would fail you in gym class. Right?
Feelings are not hurt.
I think it's feelings.
Everyone will pass if you do your work.
That's not my policy.
Even if you can't make a layup, you still pass.
You hurt my feelings, you fail. I'm so glad I'm recording this. Hi, Mrs. Jellink, the principal. I'm just joking. Okay. So anyway, I've never failed a student because they were mean to me. Yeah.
Is the name for each month?
Sorry?
Is the name for each month like patent or claimed?
Do you want to like change one?
Yeah.
Are you really hoping for like Matthew Vember, Samanjan Tuck a lie? Orlando Vember does have it's got a ring to it. Okay, anyway, so the last thing we want to talk about with the moon is the phases of the moon. And there's a couple videos here. I'm not going to show you them both. And which one do I like better? You can watch the other one on your own time. I think I like this one. But the idea of the phases, before we watch the video, I'm going to try my best to do a stupid little diagram. Ready? Okay, right? I know, I'm good. So here's the Earth. There's the Earth. And we're going to draw the sun, and the sun is here. Okay? Now you might say, why is the sun smaller than the Earth? Because it's further away. Stop criticizing me. Okay. So it's like how his face looks bigger than that building right now, even though his face isn't really bigger than the building. He's just closer to me. Okay. So now, if we were to take the moon's orbit, and we kind of say, okay, here's the orbit that the moon is going to follow around the Earth. When the moon is here, one side of it's going to be nice and bright. Which side is that? That's going to be like this side here that's facing the sun, right? And one side is going to be really dark. Hey, but if you're on Earth right now, if this is my eyeball, well, that's disturbing. I wish I hadn't drawn it like that. But if I'm looking at the moon right now, what am I seeing? To me, the moon would just look all dark, right? Does that make sense? I wish I had never drawn that. Okay, we're going to undo that.
You're looking at an eclipse.
So we see it all dark. Not an eclipse necessarily. We'll talk about eclipses. I mean, I'm not going to talk about that, but you'll have a chance to read about them. But we call this a new moon. And to us, the new moon just looks all dark. All dark. In fact, maybe I'll even go a little darker than that. And I'll be like, it looks like this. It's just really, really dark. We don't see much of anything. Yeah, that's better. See, that now it's like, now we know. Now we get it. On the other hand, if the moon is here in its orbit on the other side, well, now this side is all lit up by the sun, right? And the side that faces away from us will all be dark. What do we call that when we can only see the bright side? When from our perspective, what we would see is a moon that appears to be all bright. What do we call that?
An old moon.
Nope. Good thinking. A full moon. Yeah, a full moon. You've seen a full moon before. No. What if the moon were here in its orbit? Now, half of it is going to be bright like this. Half of it is going to be dark like that. And so we would kind of see it looking like this, where it would appear to be kind of half dark and half light. And what do we call that? Does anyone know? Because it rotates this way, right? Because it's anti-clockwise as seen from above, we call this the first quarter. And then over here, and do I have it right that that is the bright side, so we would see the bright on that side? Yeah, okay. And then on this one, we're going to see basically the same thing. You know, going to look like that. And first quarter, second quarter is a full moon. This is the last. Yeah, or the third quarter. Sometimes they call it the last quarter. Both are fine. And then here would just be moving between it. Here is going from full to that. So if we look here, you're going to see it mostly full, but starting to get towards there. By the time we get to here, what's it going to look like to us? Yeah, and I suppose I should draw them in orbit, because they're always the same, right? It's not that the moon is doing something different, it's that what we're seeing is different. So like that looks like that and like that. But this is where we will see what we call crescent moons, where our observation of this would be mostly very visible with a little bit not, and our observation of this would be mostly dark with just a little sliver visible. And you'll see the same thing here. Mostly dark with just a little sliver. Just a little sliver dark. And that is the evolution of the moon over the course of a cycle. Does that kind of make sense? Again, it's not that the sun and the moon are doing anything different. It's that they're moving relative to us. That's a clunky drawing. Don't worry about drawing it because I gave you that diagram here too. And it's much nicer than mine. But let's watch this, and then I'll be quiet. Oh, fancy animation. I need to make one of those for me. That's fun. I feel like if I had one like that and it was like Joe, everyone would be like, this guy knows what he's talking about. Oh, I don't want to know about...
That's a great looking moon.
2 ads?
Unskippable.
2 ads? 2 unskippable ads? Who's Jared think he is?
Each time you look at the moon, it's going to look a little different. Sometimes you'll see the entire moon. Other times you'll see just a portion of it. In this video, I'd like to go over why the moon looks the way it does, and a few other things about the moon's orbit. The moon takes about a month to orbit the Earth. The sun can only shine on half the moon at any given time. Since the moon orbits at exactly the same rate as it spins, we only see one side of the moon from the Earth. The side we don't see is usually called the far side of the moon. You can also call it the dark side of the moon, but it's not always dark, so this name can be a bit confusing. I'm going to show a split screen here to show things from two different views. On the left-hand side of the screen, I'll show a top-down view. On the right-hand side of the screen, I'll show what it looks like from Earth. When the moon is closest to the sun, the side of the moon facing the Earth is dark. The sunlight reflects off the Earth, so we can still see the moon if we look closely. We refer to this as a new moon. As the moon comes around, we start to see a tiny sliver of the moon. This is called the Waxing Crescent. A few more days pass by, and now we can see half the moon. We can call this a half moon, but more specifically it's called a first quarter, because we are a quarter of the way through the phases. A few more days, and only a small portion of the moon is not lit up. This is called the waxing gibbous. When the moon is on the other side of the Earth, it is completely lit. This is called a full moon, and it's probably the phase that you're most familiar with. Now the light begins to fade. We mirror the previous phases. Here's the waning gibbous, the third quarter, the waning crescent, and back to a new moon. Here's some tricks to remembering the phases. Waxing means the sunlit portion is increasing. Waning means the sunlit portion is decreasing. Crescent is where the moon is mostly dark, and gibbous is where the moon is mostly lit. Let's make sure we're accurate. The Earth is rotating once a day, tilted by 23.5 degrees. I'm going to bring back my good friend Bob here, who lives in North America.
Hi, Bob.
Bob can't always see the moon. Sometimes he'll be on the opposite side of the Earth. Because of the moon's orbit, it will rise about 50 minutes later each day. Here's the neat thing. If you know what phase of the moon we're on, then you know about the right time of day or night to look for the moon. If we're currently on a full moon, then at about the same time the sun is setting, we'll be able to see the moon rise. If we're on a new moon, it will rise at about the same time the sun rises. Now let's take a look at a first quarter moon. It will rise at about noon and set at about midnight. And a third quarter moon will rise at midnight and set at about noon. So there you have it. I hope that next time you look up at the moon, you see it just a little different than you did before. If you'd like to learn even more about it.
That's great. So guys, that's great. The rest of this, I'm going to let you fill in your own descriptions. There's 2 bits on eclipses. There's videos for both. So I won't bore you by talking your way through it. It really is self-directed stuff. And then there's some follow-up questions, but that's it for new content for this week. So this week, 3.1, 3.2, and 3.3, and you're caught up. It's a fair amount of work, but it's not, I hope it's not like an overwhelming amount. I want this unit to be more interesting than it is punishing. And then next week, the workload is really just a few quick things. It's one big project, basically, next week. So yeah, I hope that's interesting.